Tonight, we're going to explore one of the most unforgiving truths in modern science. The space beyond our atmosphere is not simply empty or distant. It is actively hostile to the human body, attacking every system that biology depends on the moment protection fails. At sea level, the air around you presses on every inch of your skin at 14.7 pounds per square inch. Across the surface of an adult body, that adds up to more than 43,000 pounds of force, over 20 tons, holding your tissues in their proper shape. In the vacuum of space, that pressure vanishes. The effects begin in less than 1 second. Gases trapped inside the body expand. Fluids start to boil at body temperature. Lungs, blood, and soft tissue all react before the mind has time to register what is happening. An unprotected human dies in roughly 2 minutes. By the end of tonight, you're going to understand what vacuum actually does to a body in those first seconds, how radiation and temperature extremes compound the damage, and why the engineering that keeps astronauts alive reframes Earth itself as a fragile biological refuge. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Think about what it takes to keep a human being alive. The list is shorter than most people expect. Breathable air, drinkable water, food, a temperature range narrow enough that the body's chemistry still works, and protection from the kinds of radiation and exposure that would otherwise tear through cells, and DNA without pause. That is the full list. A small set of conditions, and for almost every moment of human history, Earth has supplied all of them without being asked. The atmosphere sits at roughly 21% oxygen. Not so little that cells starve, not so much that tissues become toxic. Exactly the band in which human biology runs cleanly. The temperature range at the surface allows water to stay liquid, which means the body's internal chemistry has the medium it needs. Gravity holds the atmosphere in place and pulls fluids through the body in the directions the cardiovascular system expects. The magnetic field deflects streams of charged particles that would otherwise reach the surface. The ozone layer absorbs the ultraviolet radiation that would otherwise break down the molecular bonds inside living tissue. None of this requires human effort. It simply is. The body does not maintain any of these conditions. It inherits them. And here's the thing most people overlook. Human biology does not merely benefit from these conditions. It assumes them. The cardiovascular system calibrates its pressure gradients to them. The respiratory system times its mechanics to them. The cellular chemistry runs its balances against them. These are not backup systems or adaptive responses. They are the factory settings, the operating environment the body was built for and has never needed to question. Deep space provides none of them. Not some of them, not most of them, none of them. This is where the intuition of most people fails. The word space implies emptiness, and emptiness implies neutral. A vacuum feels like nothing, which the mind tends to read as harmless. But deep space is not neutral. It is actively hostile. Every protection the body has always relied on simply ceases. The defaults do not degrade gradually. They do not thin out over time. They disappear. And the body, which has spent every moment of its existence calibrated to those defaults, is left exposed in ways it has no mechanism to handle. The first default most people think of is oxygen. That is a reasonable place to start. But there is another default operating right now that almost no one thinks about. One that is just as fundamental and far more immediately violent when it disappears. Pressure. At sea level, the atmosphere presses down on every inch of exposed surface at 14.7 pounds per square inch. That is 101,000 pascals, the scientific unit for pressure. Those numbers can feel abstract, so consider what they mean across an entire body. The surface area of an adult human is roughly 20 square feet. Multiply that surface by 14.7 pounds per square inch. The total comes to approximately 43,000 pounds of atmospheric force pressing against the body at this moment. Over 20 tons. Think about that number. 20 tons. The weight of a loaded semi-truck. Pressing continuously against every external surface of the body at every moment of every day without interruption. And yet no one feels it. Here is where it gets strange. The reason that 20 tons of force goes completely undetected is that the body is also pressing outward with exactly the same force. The blood, the tissues, the fluids, the air inside the lungs, all of them sit at the same pressure as the surrounding atmosphere. The external pressure pushing inward and the internal pressure pushing outward are perfectly matched. The body exists in equilibrium with the atmosphere around it, so the net force experienced at any tissue is effectively zero. This is not passive. The body actively maintains this balance. Every major biological system is tuned to function at one atmosphere of pressure. The cardiovascular system is perhaps the most obvious example. The heart generates pressure to move blood through the body, but those pressures are calibrated relative to atmospheric pressure as a baseline. The vessels, the chambers, the capillaries, all of them sized and pressurized for a world where 14.7 pounds per square inch is the floor. Breathing is even more direct. When the diaphragm contracts and flattens, it expands the chest cavity. This expansion causes the pressure inside the lungs to drop slightly below the external atmospheric pressure. That small pressure difference is what pulls air inward. Air moves from high pressure to low pressure, from outside to inside. On the exhale, the chest compresses. Internal pressure rises above external, and air flows back out. The whole mechanism depends on atmospheric pressure as the constant reference point that the lungs push against and recover from. At the cellular level, osmotic balances, the way dissolved substances and fluids distribute themselves across cell membranes, are also set for one atmosphere. The body has no version of these processes that runs correctly in a vacuum. Every system, not one or two, every system. The pressure feels like nothing because everything inside matches everything outside. But take away the outside pressure, and the match collapses. The internal pressure, which has always been balanced, suddenly has no counterpart. The body is no longer in equilibrium. It is under outward pressure with nothing pushing back. The effects begin in less than 1 second. That timeline is not an approximation. It is not a rough estimate from early theoretical models. It is the measured response of biological tissue to sudden vacuum exposure. Less than 1 second. Before the conscious mind registers that anything has changed, the body has already begun to respond to the disappearance of a pressure it never knew it needed. What that response looks like and how quickly it becomes irreversible is the first and most immediate challenge. Deep space presents to a human being. And it is only the beginning of what the void does. What pressure was holding back was not just the air outside. It was what had been quietly dissolved inside all along. Blood is not simply a liquid. It carries gases in solution, the same way a sealed bottle of soda carries carbon dioxide dissolved invisibly into the liquid under the cap. You cannot see them. You cannot feel them. But they are there. Nitrogen, which makes up roughly 78% of the air we breathe, dissolves into blood and into the surrounding tissues. Oxygen dissolves as well, though most of it binds directly to hemoglobin. Carbon dioxide dissolves into the blood on its return journey to the lungs. All of these gases are in equilibrium with the pressure around them. One atmosphere keeps them in solution. The pressure holds them quiet, invisible, and still. Think about that sealed soda bottle for a moment. The carbonation is not gone. It is held in place by the pressure inside the bottle. The moment you open it, the pressure drops, and the gas has nowhere left to go except out. The hiss. The sudden foam climbing toward the opening. The liquid threatening to overflow. That is not a violent reaction. That is simply physics. Dissolved gas responding to a sudden loss of pressure by returning to its natural state. The human body at 1 atmosphere is that sealed bottle. Vacuum exposure is opening it all at once. The medical term for what happens is ebulism, the formation of gas bubbles in bodily fluids when external pressure disappears. And in a vacuum, the pressure does not drop gradually. It does not fall from several atmospheres to one, the way a scuba diver ascends too quickly from depth. It drops from one atmosphere to essentially zero, instantaneously. There is no gradual decompression, no interval for the body to adjust. The pressure is simply gone, and every dissolved gas in every fluid responds at the same moment. Scuba divers who surface too fast experience something called decompression sickness. The bends. Nitrogen that was dissolved in blood and tissues under the higher pressure of depth comes out of solution too quickly. Bubbles form. They collect in joints, in the spinal cord, in the bloodstream. The pain can be severe. The damage can be permanent. Divers treat it as a serious medical emergency, and they are right to. But something was wrong. The bends that a diver experiences is a milder version of the same physics, separated from vacuum exposure by an enormous difference in scale. A diver might go from 3 or 4 atmospheres to 1. That is a significant drop. Enough to pull nitrogen out of solution faster than the body can manage. Painful, dangerous, sometimes fatal if untreated. Vacuum exposure is not a few atmospheres to 1. It is 1 atmosphere to 0. Not a managed descent. A cliff. The dissolved gases in the blood do not seep out slowly. They do not migrate gradually to the lungs to be exhaled. They erupt, simultaneously, throughout every fluid in the body at once. The bloodstream, the saliva, the fluid around the eyes, the fluid in the joints, the tissue itself. The gas that was held quietly in solution by the pressure of 1 ordinary atmosphere comes out everywhere, all at once, with nothing to stop it. The blood foams. That is not a metaphor. That is the physical description of what happens when gas bubbles form faster than the circulatory system can clear them. The heart, which is calibrated to pump liquid, is suddenly pushing foam. The mechanical efficiency of every beat drops. Circulation begins to fail, not because the heart has stopped, but because what it is circulating has changed state. The damage runs in 2 directions at once. First, there is mechanical damage. Gas bubbles expand inside tissues, and tissue does not stretch comfortably around a growing pocket of gas. Vessels can be blocked. Tissue can tear. The expanding gas exerts pressure from the inside, the same outward pressure that now has no counterpart from without. Second, there is circulatory damage. Blocked vessels mean that oxygenated blood cannot reach the cells that depend on it. The foam in the heart means delivery pressure is falling. Both processes are happening in the same body, in the same second, feeding each other. The swelling that results is visible. Documented cases of individuals accidentally exposed to near-vacuum environments, in testing facilities, and in one documented event during a spacesuit failure in 1966, describe rapid inflation of the limbs and body. The tissues swell as gas expands inside them. One researcher who briefly lost pressure in a spacesuit during a vacuum chamber test reported feeling the saliva on his tongue begin to boil before he lost consciousness. Not boil from heat, boil from the drop in pressure. The same principle that makes water boil at a lower temperature at high altitude. Reduce the pressure enough, and liquid changes state at body temperature. The body, in vacuum, fizzes from the inside. That is the reality of embolism. Not a dramatic external injury, not a wound. A quiet, cellular-scale dissolution of the chemistry that was running correctly 1 second before. The physics that held the gases dissolved was the same physics that held everything else together. Lose one, and you lose both. And embolism is only the first thing that begins in that first second. The gases coming out of solution are the fastest consequence of pressure loss. But the tissues themselves and the fluids they depend on are already beginning to respond to the same lost equilibrium in ways that run deeper and last longer. And while that is happening, something else is happening in those same fluids. The gases are coming out of solution, yes, but the liquids themselves are also trying to leave. Both processes begin at the same instant, Both processes involve the same lost equilibrium. The body is not failing in one way, it is failing in two ways simultaneously, and understanding the second one requires going back to something most people think they already understand. Water boils at 212 degrees Fahrenheit, at sea level. That last part matters more than most people realize. The boiling point of water is not a fixed property of water. It is a negotiation between the energy of the water molecules and the pressure of the air pushing down on the surface. At sea level, that air pressure is substantial. Water molecules need a lot of energy to escape the liquid state against that pressure. So the temperature has to reach 212 degrees Fahrenheit before they can. Now, climb. At the summit of Mount Everest, the atmospheric pressure drops to roughly 1/3 of what it is at sea level. The air pushing down on the surface of a pot of water is weaker. The water molecules do not need as much energy to escape. They boil at about 154 degrees Fahrenheit up there. Not 212. A full 58 degrees lower. Not from more heat. From less pressure. That is the principle. Now follow it to its conclusion. In the near vacuum of space, the atmospheric pressure pushing down on any liquid surface approaches zero. The molecules in the liquid need almost no energy at all to escape. They can leave the liquid state at any temperature above absolute zero, which is minus 459 degrees Fahrenheit, the coldest anything can physically be. Body temperature is 98.6 degrees Fahrenheit, which is 37 degrees Celsius. That is not close to absolute zero. That is, in thermodynamic terms, a warm and energetic state. In vacuum, body fluids boil at body temperature. Not because the body is overheating, because the pressure holding those fluids in their liquid state has vanished. The saliva on the tongue boils. The moisture coating the surface of the eyes evaporates into vapor. The fluid in the lungs bubbles and froths. This is not a Hollywood image of bodies exploding or rupturing from internal pressure. It is quieter than that, and in some ways more unsettling. It is flash boiling, molecules releasing from liquid into vapor and dispersing. The surface of the tongue goes dry and then does not feel like a tongue anymore. The eyes, within seconds, are no longer seeing clearly. The lungs, already dealing with expanding gas from ebulism, are simultaneously filling with foam from their own moisture-changing state. Vacuum chamber experiments with water confirm this. Place a small dish of water in a vacuum chamber and evacuate the chamber. The water does not wait to be heated. It boils immediately, at room temperature, and disappears into vapor. The pressure removed, the liquid cannot hold itself together. This has been confirmed with water many times. Not with living subjects for obvious reasons. But the physics applies to any liquid, and blood and saliva and joint fluid and the moisture in the lungs are all, at their base, water. The picture did not hold. The lungs face a third problem on top of ebulism and vapor phase boiling. They contain air, normally about 6 liters of it. 6 liters is roughly the volume of a large pot, the kind you would use to boil pasta. In a pressurized environment, that air is held inside at a pressure matching the outside world. In vacuum, the outside pressure drops to nothing. The air inside the lungs has nowhere to push against. It tries to expand, to fill the available space. There is no available space in the lungs. The lungs expand as far as their tissue will allow, and then the tissue tears. The instinct to hold your breath in a dangerous situation is deeply wired. It is wrong here. A scuba diver who holds a breath and ascends from 10 meters underwater to the surface experiences a pressure drop of roughly 1 atmosphere. That is enough to rupture lung tissue. That is a documented, well-understood injury in diving medicine. Scuba instructors make this one of their earliest and most emphatic warnings. Never hold your breath while ascending. 1 atmosphere of change can do serious damage. Vacuum exposure is not 1 atmosphere of change. It is 1 atmosphere to 0. The entire pressure differential at once. Holding your breath in vacuum does not protect you. It accelerates the injury. The air inside has nowhere to go. The lungs rupture in the first seconds. exhaling before exposure has been considered. It is not a solution. Exhaling empties the lungs of some of that expanding air. It buys a few seconds at most. The ebulism has already begun before the first breath is exhaled. The vapor phase boiling of body fluids has already begun. Exhaling is the right move if the choice exists, because it reduces the lung rupture risk slightly. But the word slightly is doing a great deal of work in that sentence. The body is already in cascade failure by the time the exhalation is complete. Now consider the environment where all of this happens. The word vacuum tends to conjure a picture of perfect emptiness. Space as a pure and absolute nothing. That picture is not quite accurate. Space is not perfectly empty. Even in the quiet stretches between star systems, where there are no planets, no dust clouds, no visible structure of any kind, the interstellar medium still contains matter. A few atoms per cubic centimeter on average. Hydrogen mostly. Occasionally helium. Here and there something heavier. A few atoms. That is close to nothing, but it is not nothing. Think about the difference in scale. Earth's atmosphere at sea level contains roughly 10 to the 19th power molecules per cubic centimeter. That is 10 billion molecules in a space the size of a sugar cube. Interstellar space contains a few atoms in that same space. Put another way, if the atmosphere at sea level were a city of 10 billion people, interstellar space would be a continent with one person standing somewhere on it. Not 2 or 3 people. 1. Near Earth. In the low orbital zone where the International Space Station travels at about 250 miles up, the density is higher than in deep interstellar space. There are more molecules per cubic centimeter at ISS altitude than there are between the stars, but not many more. The atmospheric pressure at ISS altitude is roughly 1 trillionth of sea level pressure. 1 trillionth. That residual atmosphere is thin enough that it causes measurable drag on the station over time. Without periodic engine firings to reboost its altitude, the station would gradually spiral inward and burn up. The air is real. It has physical consequences for an orbiting object. But for a human body, 1 trillionth of sea level pressure and 0 pressure are the same thing. The difference between them is a footnote in the physics. It is not a footnote in the biology. Every process described in the last several minutes begins at ISS altitude, exactly as it would begin in the deep void between stars. The body cannot distinguish between an almost perfect vacuum and a perfect one. The threshold for physiological response is crossed long before you reach either. And the consequences do not stop with the fluids. The pressure and the chemistry of the fluids were holding something else together too. Something that most people never think about when they think about survival in space. Something that most people never think about when they think about survival in space is what the brain needs to keep the experience of being alive running at all. The brain is a small organ. It accounts for roughly 2% of the body's weight, but it consumes about 20% of the body's oxygen. Every minute, every second, it draws on a disproportionate share of what the lungs bring in. The rest of the body can endure oxygen deprivation for meaningful stretches of time. Muscles can go anaerobic for a while. Tissues can hold on. The brain cannot. Brain cells begin dying within seconds of oxygen deprivation. Not minutes, seconds. In ordinary conditions, a person can hold their breath for roughly a minute without training. 2 minutes with training. And during that entire window, the blood is still oxygenated. The lungs still hold residual air. The body is running on a depleting reserve, but it is running. The brain has something to work with. In vacuum, none of that applies. The lungs empty. Expanding gases escape. The pressure differential forces air out through the mouth and nose whether the person intends it or not. And the bloodstream, by this point, is already compromised. Ebulism has begun. Gas bubbles are forming in the circulatory system. The heart is no longer pumping clean blood. It is pumping foam. What it is circulating through the body can no longer carry oxygen effectively, even if oxygen was somehow available. The delivery system has failed. The brain receives nothing. Consciousness fades in roughly 10 to 15 seconds. That is the duration of a single, slow, deliberate exhale. That is a brief moment of looking up at something before looking away. It is not a long struggle. It is not a gradual dimming. It is fast. And once consciousness goes, the damage does not pause. Brain damage accumulates over the following minutes. Complete brain death follows within 4 to 6 minutes of oxygen cutoff. Not recovery, not a haze. Permanent cellular loss, accumulating irreversibly from the moment the supply stops, and the bubbles make it worse. Gas emboli, meaning gas bubbles blocking blood vessels, cut off circulation to regions the heart is already struggling to reach. The circulatory system is not just carrying compromised fluid, it is carrying fluid that is partially obstructed, partially blocked, delivering less to tissues already starved. The collapse is not a single event. It is a cascade of overlapping failures, each one accelerating the next. Here is the thing that changes how rescue gets calculated. Every second past the first few seconds of exposure adds to a damage total that cannot simply be reversed by repressurization. Immediate rescue, within the first 10 to 15 seconds, offers a meaningful window. Beyond that, the window narrows fast. The body can be brought back to pressure. The gases can redissolve. The fluids can return to their liquid state. But the brain damage that accumulated during those minutes does not undo itself. Repressurization restores the environment. It does not restore what was lost inside the cells while the environment was gone. The picture assembled across the last several minutes is not a single cause of death. It is 3 processes happening simultaneously, feeding each other: pressure loss, embolism, and now, layered over both, neurological collapse from oxygen starvation. Each one would be dangerous alone. Together they converge in a window measured in seconds. But here is where it gets strange, because most people, when they think about dying in space, are not picturing any of those 3 things. They are picturing the cold. Space is cold. That is not wrong. The image most people carry is of a body freezing instantly, flash frozen in the void, solid in seconds. That image is in dozens of films. It has become a kind of default assumption, and the assumption contains real physics. Space is extraordinarily cold, but the cold does not work the way the image suggests. Start with what the temperature of space actually means. Temperature, in the ordinary sense, measures the motion of molecules. Molecules moving fast means high temperature. Molecules moving slowly means low temperature. In a vacuum, there are almost no molecules. Not a few. Not a sparse population. Almost none. The concept of temperature, in the usual sense, begins to lose meaning. There is not enough matter to carry thermal energy in the way the word implies on Earth. What does exist is thermal radiation. Specifically, the cosmic microwave background, the faint remnant energy left over from the early universe, fills all of space at roughly negative 454.75 degrees Fahrenheit, which is negative 270.42 degrees Celsius. That is a few degrees above absolute zero, which sits at negative 459.67 degrees Fahrenheit. The difference is real, but small. Space is, in radiative terms, extraordinarily cold. Now consider how heat actually leaves a body. On Earth, heat moves 3 ways. Conduction is direct contact, the warmth that leaves your hand when you press it against a cold surface. Convection is movement through a fluid medium, the way cold air carries warmth away from skin on a winter day. Radiation is the emission of infrared light, the heat that glows outward from any warm object. In vacuum, conduction does not operate. There is nothing to touch. Convection does not operate. There is no medium to carry warmth away. Only radiation remains. Think of a thermos. A thermos works by removing conduction and convection from the equation. The vacuum between the walls eliminates both. What keeps a thermos from being perfect insulation is that radiation still moves through vacuum. Even without molecules, infrared light travels freely. The thermos slows heat loss dramatically. it does not stop it entirely. A body in vacuum is in a similar position. Stripped of conduction and convection, it radiates heat outward through infrared emission. But radiation at body temperature is slow. A body at 98.6 degrees Fahrenheit emits infrared light constantly. Over hours, that radiation would extract enough heat to cause hypothermia. Over a long span, it would cause death from cold. But it would take hours, not seconds, not instant freezing. Hours of gradual cooling. Pressure kills in under a second. Oxygen ends consciousness in 10 to 15 seconds. Cold, left to its own pace, would take hours to reach a lethal threshold. By the time the temperature became the problem, everything else would have long since ended. The cinematic version has the sequence backwards. Cold is real. Cold is eventual. Cold is not the immediate killer. It is the slowest threat in the sequence. But that is in deep space, away from a star. Near a star, the temperature problem inverts entirely. Close to the Sun, in the region where Earth orbits, the solar constant, the rate of solar energy arriving per square meter, sits at approximately 1,361 watts per square meter. That is a significant energy flux. Without an atmosphere to distribute it, without convection to move heat around the body, that energy lands on one side and stays there. The sun-facing side of a body in open space near Earth's orbit could exceed the boiling point of water. The shadow side, shielded from direct solar radiation and radiating its own heat outward into the cold background of space, could drop well below freezing. Both conditions would exist simultaneously, across the width of a human body. The gradient between them would be extreme, not a temperature to adapt to. A split with one side baking and the other freezing, and no atmosphere anywhere to even the difference. Cold as an instant killer was always the wrong frame. The real picture is more complicated, and in some ways more extreme than the simple image. And the extremity does not end with temperature. The sun has been doing something else this whole time. The warmth was only part of it. The light pressing against one side of a body in open space near Earth, heating skin toward the boiling point of water while the shadow side freezes, carries another layer that thermal measurements alone do not capture. That energy is not just heat, it is radiation. And radiation, in the full sense of what that word means in space, is a different category of danger from anything discussed so far. On Earth, that danger is mostly invisible to daily experience, because the planet has built 3 separate shields to absorb it. The first is the atmosphere itself. The miles of air above every surface do not just provide oxygen and pressure. They absorb enormous portions of the energy arriving from the sun and from the cosmos. The second is the magnetic field. Earth generates a powerful magnetic envelope that deflects charged particles arriving from the sun and from deep space, bending their paths away from the surface and funneling them toward the poles. When those particles collide with the upper atmosphere near the poles, the energy releases as light. That is what the northern and southern lights are. Auroras are not decorative. They are the visible evidence of a collision that would otherwise reach the ground. The third shield is the ozone layer, a thin region of the upper atmosphere where oxygen molecules in a particular configuration absorb ultraviolet radiation before it can reach the surface. 3 separate systems, each catching a different category of threat. Remove all 3 at once. That is what space does. The electromagnetic spectrum runs from radio waves at the low energy end through microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays at the high energy end. The low energy portions reach Earth's surface and support life. Visible light makes photosynthesis possible. Infrared warms the ground. But above visible light on the energy scale, the spectrum becomes progressively more damaging to biology. Ultraviolet radiation at Earth's surface is already filtered. Most of it is absorbed by the ozone layer. What gets through, primarily the longer wavelength UVA and some UVB, is enough to cause sunburn and long-term skin damage. The shorter wavelength UVC, the most biologically damaging form, is fully blocked by the ozone layer. No one at ground level is ever exposed to it. In space, there is no ozone layer. The full ultraviolet spectrum arrives without filtration. UVC, the wavelengths that never reach the ground, hits directly. Unprotected skin exposed to the full solar UV output in space would begin accumulating DNA damage within minutes. Not sunburn. Cellular damage. Strand breaks in DNA. Disruption of the molecular machinery that governs how cells reproduce and function. But UV, serious as it is not the deepest problem. Solar flares and coronal mass ejections, eruptions from the sun's surface that release enormous bursts of energy and charged particles, produce X-rays and gamma rays. These are far higher up the energy scale than UV. They penetrate materials that UV cannot reach. They pass through unshielded bodies in space. During a major solar particle event, a burst of this high-energy radiation can arrive at spacecraft position within hours. During the Apollo missions, astronauts traveled beyond Earth's protective magnetic field and into unshielded space. No major solar particle event occurred during any of the Apollo missions. That was not planning. That was chance. Mission planners now design spacecraft with storm shelters, areas of concentrated extra shielding that crews can move to during a solar event. The shelters reduce dose. They do not eliminate it. And solar particle events, as serious as they are still not the deepest problem. But the reality was different. Beyond the sun, beyond the solar system, the galaxy itself is constantly firing particles through the entire volume of space. These are galactic cosmic rays, and they are not electromagnetic radiation in the way light or X-rays are. They are matter. Atomic nuclei, protons and helium nuclei, and heavier elements including carbon, oxygen, and iron, stripped of their electrons and accelerated to extraordinary speeds by the most violent events in the universe. Supernovae, the explosive deaths of massive stars, neutron stars spinning at hundreds of revolutions per second, black holes accelerating surrounding matter to relativistic speeds. These events are not nearby. They are distributed across the galaxy. The particles they launch travel the galaxy for millions of years before eventually passing through this region of space. The speed of these particles is around 90% of the speed of light. That number deserves a moment. Particles in the most powerful accelerators humans have ever built reach high fractions of light speed under carefully engineered conditions. A single galactic cosmic ray nucleus carries kinetic energy millions of times higher than particles in those machines. The machines are kilometers in circumference and require enormous amounts of energy to operate. The cosmic ray is a single atomic nucleus that simply arrives from deep space. No machine produced it. No mechanism here can stop it. When such a particle strikes human tissue, it ionizes atoms along its path. Ionization means stripping electrons from atoms, breaking chemical bonds, disrupting the molecular structures that cells depend on. The particle does not slow down meaningfully as it passes through. It carves a narrow track of destruction through whatever material it crosses. DNA is a specific and critical target. A single cosmic ray hit can break a DNA strand outright, killing the cell. Or it can produce a mutation, a change in the genetic code that does not kill the cell immediately, but alters how it reproduces. That is a cancer mechanism. A single particle, a single hit. At Earth's surface, behind the magnetic field and the atmosphere, a few cosmic rays per square centimeter arrive every second. Most pass through the body without hitting anything critical. The body's repair mechanisms handle most of the damage. The dose is low enough that it accumulates slowly across a lifetime. In space, the flux is hundreds to thousands of cosmic rays per square centimeter per second. The magnetic field is gone. The atmosphere is gone. The particles arrive from all directions, not just from above. ISS astronauts are partially shielded, because the station orbits within the edge of Earth's magnetic field. Even with that partial shielding, ISS astronauts receive approximately 150 to 200 times the radiation dose of someone on the ground. A 6-month ISS mission increases a person's lifetime cancer risk by roughly 1%, borderline acceptable for trained volunteers operating in a known risk environment. A round-trip Mars mission, which requires approximately 18 months to 2 years of travel time, increases lifetime cancer risk by approximately 5%. 5% from radiation alone, before accounting for any other hazard. That sits at the outer edge of what regulatory frameworks for occupational radiation exposure have historically considered acceptable, and Mars is the nearest planet. Cancer risk is not the only concern. Animal studies using particle beams designed to approximate cosmic ray exposure have produced effects on the central nervous system. Brain structural changes, memory impairment, reduced problem-solving performance, increased anxiety behaviors. Whether these findings translate directly to humans is still being studied, and the translation is genuinely uncertain. But the stakes are not abstract. On a long mission, cognitive sharpness is not optional. A crew facing a systems failure or an emergency landing requires full problem-solving capacity. Radiation that degrades that capacity in ways that accumulate invisibly over months is a threat of a different kind than a hull breach. The obvious question is shielding. Build thicker walls. Add mass. Surround the crew in material that absorbs the particles. But here, the physics introduces a constraint that does not yield to engineering in any straightforward way. Cosmic rays can penetrate meters of material. A few millimeters of aluminum hull, the thickness of a typical spacecraft wall, provides almost no protection. Thicker aluminum would help against lower energy particles, but for the highest energy cosmic rays, it creates a new problem. When a high energy cosmic ray nucleus strikes an aluminum nucleus, the collision can shatter both, producing a spray of secondary particles that are themselves biologically damaging. More aluminum can mean more secondary particles. The shielding becomes part of the source of harm. Water and other hydrogen-rich materials are better. Hydrogen nuclei are small and light, and they absorb cosmic ray energy without producing the same cascade of secondaries. A wall of water reduces the problem more effectively than a wall of aluminum. But effective cosmic ray shielding requires meters of water. Meters of water is thousands of kilograms of mass. Every kilogram of mass launched from Earth requires propellant in an exponentially growing ratio. The rocket equation governs all of this. The mass required to shield adequately against cosmic rays, carried as water or hydrogen-rich material, would add so much to a spacecraft's mass that the mission becomes nearly impossible to launch with any foreseeable technology. There are mitigations. Timing missions to solar minimum, when the sun's own magnetic field is weaker, but also when it provides somewhat less additional cosmic ray exposure from solar events. Building storm shelters for solar particle events. Limiting mission duration to keep total dose below the highest risk levels. These strategies reduce the numbers. None of them eliminate the exposure. Radiation is not a problem waiting for a clever engineering solution. It is a constraint imposed by the physics of the universe itself. The source is the entire galaxy. The particles have been accelerating for millions of years. They arrive from every direction. They penetrate everything. More shielding has diminishing returns and can worsen secondary particle production. Less time in space means less exposure, but the physics of orbital mechanics requires that interplanetary missions take a minimum amount of time regardless of how fast the spacecraft travels. The question of whether foreseeable technology can adequately mitigate long-duration deep space radiation effects remains genuinely open. And radiation, for all its invisibility, may be the most stubborn of the constraints standing between human biology and the outer solar system. It is not the last one. All of that brings us back to one body, one moment, 1 second of pressure loss, and the cascade we have spent the last hour tracing begins. Let's watch it unfold from the beginning, 1 second at a time. At 0 seconds, the pressure drops. From 1 atmosphere to near nothing, instantly. Every physiological system calibrated to that pressure is now operating in conditions it was never designed for. At 1 second, the air in the lungs expands. If the person has held their breath, the expanding air has nowhere to go. Lung tissue tears. If they are exhaling, the air rushes out and the damage is reduced, but only slightly. The damage elsewhere is not reduced at all. Saliva on the tongue begins to boil, not from heat, from pressure loss. The same physics that lowers water's boiling point at altitude is now operating across every wet surface in the body. The eyes begin to lose their moisture. The mouth and nasal passages are doing the same. At 2 seconds, ebulism is happening throughout the bloodstream and surrounding tissues. Gas bubbles are forming everywhere dissolved gases are held. The skin begins to swell as subcutaneous gas expands outward. The body is, by this point, something that would be almost unrecognizable to watch. Around 4 seconds, something briefly strange occurs. The water vapor from all that boiling moisture cools the mouth and nasal passages as it evaporates. There is a momentary sensation of cold, a brief, strange coolness in the throat and sinuses. It lasts less than a second. Then the swelling overtakes it. At 6 seconds, circulation is already compromised. The bubbles forming in the bloodstream are blocking vessels, preventing oxygenated blood from moving where it needs to go. At 8 seconds, the brain and organs are consuming the last of the oxygen already in the bloodstream. No new oxygen is entering. The lungs are functionally empty. The blood delivering what remains is increasingly foam rather than clean fluid. At 10 seconds, the brain's oxygen supply drops below the threshold required to maintain consciousness. Vision narrows. The edges of sight compress inward. Hearing fades. At 12 seconds, consciousness is lost. From this point on, the person experiences nothing further. That is worth pausing on. Not a slow fade, not a struggle, not the long, agonizing ordeal that decades of science fiction have burned into every viewer who has ever watched a film set in space. 12 seconds. Roughly the time it takes to read 3 sentences aloud. After that, the person is no longer present for what follows. What follows is this. Around 15 seconds, the heart is still beating. It is pumping bubble-laden blood through increasingly compromised vessels, but the mechanical function has not yet stopped. Brain activity is declining rapidly. At 30 seconds, the body is visibly swollen. Tissue everywhere has expanded from the gas accumulation. Blood pressure is erratic. At 60 seconds, the brain damage from oxygen starvation has become irreversible. Even if the person were repressurized at exactly this moment, with immediate medical intervention, the neurological damage would almost certainly be severe and permanent. At 90 seconds, cardiac function is failing. The heart is still attempting to beat, but weakly, irregularly, against a circulatory system that is no longer carrying the medium it was built to move. Brain activity has mostly ceased. At 2 minutes, it is over. No heartbeat, no brain activity. Clinical death in the precise medical sense of the term. That is the timeline, not drawn from speculation, drawn from animal experiments in vacuum chambers, from known physiology, and from one documented case of a human being who actually survived. In 1965, a technician at the Johnson Space Center was testing a spacesuit inside a vacuum chamber when the suit failed. He was exposed to near vacuum conditions for approximately 14 seconds before the chamber was repressurized. He reported 2 things before he lost consciousness. The saliva on his tongue was boiling. Then, the world went away. After repressurization, he regained consciousness. He recovered fully. No lasting damage. That case is not a footnote. It defines something important. 14 seconds is approximately the upper boundary of survivable vacuum exposure. And it was survivable only because repressurization was immediate and medical care was available within seconds, and the chamber was already designed to be repressurized quickly. In actual deep space, none of those conditions exist. There is no chamber. There is no technician on the other side of the wall. The boundary of survivable exposure is 14 seconds under the best possible rescue scenario. Without rescue, 2 minutes. The cinematic image, the one where an astronaut drifts slowly in space, struggling for a minute or more, reaching out, still conscious, still present for their own death, is fiction. Not an exaggeration, not a dramatization. The reality compresses the entire experience into roughly 12 seconds of awareness, followed by 90 seconds of biological machinery winding down in a body that no longer contains anyone. Now the question shifts. What happens after that? What becomes of a body in space, not in minutes, but over years? On Earth, we know the answer. Decomposition is a biological process that requires ingredients, environmental bacteria, insects, oxygen, moisture, warmth. Take those away and the process stalls or stops. In space, most of those ingredients are absent. There are no insects. There are no environmental bacteria landing on the surface. The internal gut bacteria that colonize a living body continue to function briefly after death, producing gases as they break down tissue. But with no atmospheric pressure to contain those gases, they escape immediately. The internal biological process that drives early decomposition on Earth dissipates almost as soon as it begins. What takes over instead is sublimation. The water in the body's tissues does not melt and then evaporate, because there is no liquid phase available at near zero pressure. The moisture in the tissues freezes and then converts directly from solid ice to vapor, bypassing the liquid state entirely. The result, over days and weeks, is a freeze-dried body. The same process used to preserve food for long-duration storage, except applied to an entire human being by the physics of the void. If the body is in sunlight near a star, the sun-facing side may warm enough for some additional chemical breakdown. But the shadow side remains frozen. Far from any star, the body reaches the deep background temperature of space and stays there, frozen solid, indefinitely. Over longer timescales, ultraviolet radiation and cosmic rays, both familiar from the previous hour, continue to do their work. The same UV that breaks DNA strands in living cells slowly dismantles organic molecules in dead ones. The same cosmic rays that alter brain structure over a 6-month mission are still arriving, still ionizing, still breaking chemical bonds in whatever material they pass through. Over millions of years, the body degrades, organic molecules break apart, atoms drift free, the complex structure that was a human being dissolves into its components. But for years to come, and likely for decades, the body would remain largely intact, frozen, desiccated, recognizable. The normal biological processes that govern life and death on Earth assume Earth. They assume bacteria in the soil, moisture in the air, insects, oxidation, warmth, gravity drawing fluids down through tissue. Remove Earth, and the process that has governed the fate of every living thing for the entirety of biological history simply does not run. A body in space does not decay the way a body on Earth decays. It enters a different kind of time, which is a reminder of something that has been running beneath the surface of everything we have covered. The human body does not merely prefer Earth conditions, it requires them, not as a baseline to improve upon, as the only context in which it functions at all. Every failure mode we have traced, the pressure cascade, the ebulism, the oxygen starvation, the radiation damage, the thermal extremes, follows from the same underlying fact. Human biology is a system precisely calibrated to one planet. Change the planet, and the system stops. That is not a problem with the body. It is a description of what the body is, and it is where the engineering challenge begins. The engineering challenge begins with a simple question. What does a human being actually need to stay alive? And how do you carry all of it on your back? A spacesuit is not protective clothing. That framing undersells it by an enormous margin. A spacesuit is a spacecraft. A miniature, wearable spacecraft, with every system a human body requires packed into roughly 280 pounds of layered fabric, metal joints, tubing, tanks, and electronics, pressure regulation, oxygen supply, carbon dioxide removal, temperature control, communications, power, each one independently capable of killing you if it fails. Each one running simultaneously, every minute of an EVA, a spacewalk outside the station or the vehicle. Start with pressure, because pressure is the foundation everything else rests on. NASA's current suits maintain an internal pressure of about 4.3 pounds per square inch. That is well below Earth's atmospheric pressure of 14.7 pounds per square inch. But it is high enough to keep the body's fluids in their liquid state and prevent the cascade of effects covered earlier. The reason the suit runs at low pressure rather than matching Earth conditions comes down to mobility. A fully pressurized suit naturally wants to be a sphere. That is the lowest stress shape for an enclosed pressurized volume, and the internal pressure constantly pushes every part of the suit toward that shape. Bending an elbow in a pressurized suit means working directly against that force. The analogy that captures it best is trying to bend a partially inflated tire. You can do it, but it costs effort every single time, and after hours of it, the fatigue compounds. Lower pressure means the suit resists motion less, but lower pressure creates a problem. At 4.3 pounds per square inch of total pressure, the body does not automatically get enough oxygen. Here is why. Each gas in a mixture contributes its own fraction of the total pressure, proportional to how much of it is present. Earth's atmosphere is roughly 21% oxygen. At sea level, that translates to an oxygen partial pressure of about 3 pounds per square inch. The lungs need at least 2.5 pounds per square inch of oxygen partial pressure to function normally. Below that threshold, the result is hypoxia, confusion, weakness, loss of judgment, eventually unconsciousness. At 4.3 pounds per square inch total, filling the suit with the same mix of gases as Earth's atmosphere would leave the oxygen partial pressure well below that minimum. So the suit does not use a mix. It uses pure oxygen, 100%. That way, all 4.3 pounds per square inch of pressure is oxygen partial pressure, more than enough for normal lung function, while keeping the total pressure low enough that the suit remains manageable to move in. It is an elegant solution. It solved the mobility problem and the oxygen problem simultaneously. But something else was happening. Pure oxygen at elevated pressure is not merely a gas that supports combustion. It is an environment in which materials that would never ignite in ordinary air will burn readily. Fabrics, foam padding, insulation, Velcro. Things that are inert in a normal atmosphere become fuel in pure oxygen. On January 27th, 1967, 3 astronauts were sitting inside the Apollo 1 command module, not in space, on the launch pad at Cape Canaveral, conducting a routine pre-launch test. Virgil Grissom, Edward White, and Roger Chaffee. The cabin was pressurized with pure oxygen at approximately 16 pounds per square inch, slightly above atmospheric pressure, a configuration chosen for the test. A spark from faulty electrical wiring ignited nearby materials. The fire spread instantly. Within seconds, the interior of the capsule was fully involved. The hatch could not be opened in time. Its design required pressure equalization before it would move. With the interior pressure rising from the fire, equalization was impossible. All 3 astronauts were lost in less than a minute. That is not a dramatization. The entire event, from ignition to fatality, took under 60 seconds. The aftermath reshaped the program. Materials were changed. Hatch designs were changed. Protocols were changed. The pure oxygen atmosphere used in launch tests was replaced with a mixed gas atmosphere at or near sea level pressure, reverting to pure oxygen only in orbit, at the reduced suit pressure. The lesson was absorbed at enormous cost. Modern suits at 4.3 pounds per square inch carry substantially lower fire risk than the 16 pounds per square inch cabin atmosphere that night. But the vigilance has never loosened. A fire inside a sealed suit, at any pressure in any oxygen-rich environment, is immediately lethal. There is nowhere to go. Beyond pressure and oxygen lies the next problem. The oxygen you breathe does not simply disappear. The body uses it and produces carbon dioxide in return. On Earth, that carbon dioxide disperses into an atmosphere so large that the local concentration never rises to dangerous levels. In a sealed suit, it accumulates, and carbon dioxide buildup is not a slow, gradual process. At high concentrations, it produces dizziness, confusion, a sensation of suffocation, and eventually unconsciousness, in roughly the same sequence as oxygen deprivation and for related physiological reasons. The solution is chemical. Lithium hydroxide canisters. Lithium hydroxide reacts with carbon dioxide to produce lithium carbonate and water, binding the CO2 into a solid that stays in the canister and out of the breathing gas. The process is continuous and passive. No power required, no moving parts. The CO2 is simply captured and locked away. But the canisters are finite. Each one has a limited capacity. Once saturated, the chemical reaction stops, and CO2 begins accumulating again. A typical EVA runs 6 to 8 hours, and suits are loaded with enough canister capacity for that duration, with margin built in. That margin matters, because it has nearly been exhausted before. On early spacewalks, unexpected exertion or extended timelines pushed CO2 levels toward dangerous thresholds. Those close calls drove the strict time limits and monitoring protocols that govern EVAs today. Temperature presents its own engineering problem, distinct from the thermal environment of open space. The human body generates heat continuously. At rest, roughly 100 watts of metabolic heat, about the output of a moderately bright incandescent bulb. During physical work, significantly more. On Earth, that heat dissipates through convection, the movement of air across the skin, and, through conduction, the body transferring heat to surfaces it contacts. In vacuum, neither mechanism operates. Convection requires a medium. Conduction requires contact with something that conducts. The suit provides neither. Without active cooling, an astronaut working inside a pressurized suite would overheat within minutes. Heat exhaustion. Heat stroke. The suit becomes an insulated container, and the body is the heat source inside it. The solution is a liquid cooling garment, worn directly against the skin underneath the suit layers. It looks like a pair of long underwear stitched through with fine tubing. Cool water circulates through those tubes, absorbing heat from the skin's surface, then routes through a heat exchanger in the suit's backpack, where the heat is radiated away into space. The water cycles continuously. The astronaut works. The heat flows out. If that cooling system fails, the window is not long. Roughly 10 to 15 minutes before the heat buildup reaches dangerous levels. That timeline is short enough that cooling system failures constitute one of the most serious contingency scenarios in EVA planning. And then, there is the sun itself. Solar energy at Earth's orbital distance arrives at approximately 1,360 watts per square meter, about 1.8 horsepower striking every square meter of surface, every second. On the sunlit side of a suit, that energy is relentless. The outer layer of the suit is reflective white, designed to turn away as much visible and infrared light as possible. Even so, sunlit suit surfaces can reach around 250 degrees Fahrenheit. The shadow side of the same suit, turned away from the sun, can drop to roughly negative 50 degrees Fahrenheit. The gradient across the width of a human body in orbit can span 300 degrees simultaneously, with the suit managing both extremes through insulation and the active cooling system. The mobility constraints compound all of this. Joint bearings and specialized fabric designs let the suit articulate at knees, elbows, and shoulders while maintaining the pressure seal. But articulation is never free. The suit resists every movement against internal pressure all day. EVA astronauts return physically exhausted, in a way that the same duration of labor on Earth does not produce. The hands bear the worst of it. Pressurized gloves resist grip. Fine motor control is difficult when every finger movement is working against the pressure inside the glove. Reports of hand fatigue, cramping, and in some cases damage to the nail beds from repeated pressure cycles are not rare. The suit keeps the astronaut alive. It does not make the work easy. Most of the suits currently in use trace their fundamental design to the 1980s and 1990s. They have been refurbished and upgraded over the decades, but the underlying architecture is aging. New designs have been in development for years. The path from design to flight certification for a suit that a human life depends on is long and deliberately slow. Until replacements are qualified and ready, the missions continue on aging hardware. A spacesuit is a complete life support system compressed to wearable scale. Pressure, oxygen, CO2 removal, temperature, power, communications, and mobility, all running together, all depending on one another, all running inside a volume the size of a human being. Single-point failures can be lethal. The suit has to get everything right, every time, for every hour of every EVA. And the suit is only the first layer of what it takes to keep a person alive in space. The spacecraft surrounding it is the second, and the logic is the same. Mass constraints, integrated systems, single-point failures, fragility traded for capability. What changes is the scale. A suit wraps one person. A spacecraft wraps the crew, the supplies, the equipment, the air, the water, everything needed to keep people alive for days or months or years. And the same ruthless trade that made the suit what it is, made the spacecraft what it is. That trade has a name: the rocket equation. The principle is simple, and it is merciless. To get mass into orbit, you need fuel. To carry that fuel, you need more fuel. The fuel to carry the fuel adds up faster than intuition expects. The result is that only roughly 3 to 5% of a typical launch mass actually reaches orbit. The rest is propellant, burned, and discarded on the way up. Engineers learned early that every kilogram of spacecraft mass costs an enormous amount of fuel. So they removed every kilogram they could: thinner walls, lighter materials, fewer redundant systems. The spacecraft that reaches orbit is the lightest version of itself that can still hold together and sustain a crew. The walls of the International Space Station reflect that calculation. ISS module walls are approximately 3 millimeters thick. That is about 1/8 of an inch. The thickness of a few stacked credit cards. That is what stands between the crew and vacuum, not because no one thought about making the walls thicker. Because the rocket equation did not allow it. 3 millimeters holds pressure. It does not offer much else. The threats to those walls are real, and they are constant. In low Earth orbit, space is not empty. It is populated by micrometeorites, fragments of dead satellites, loose hardware, and objects as small as flakes of paint that have been drifting since the early missions. All of them are traveling at orbital velocity. A collision between two objects in orbit is not like a collision on the ground. The relative speeds are enormous, and kinetic energy scales with the square of velocity. Even a millimeter-scale fragment carries energy comparable to a bullet. A paint flake moving at orbital speed hits with enough force to chip glass, pit metal, and crater a surface. The ISS windows carry the evidence. Some of those craters are visible to the naked eye. The station has been struck many times, no catastrophic breach so far. But the risk is not zero, and it does not go away. Known objects can be tracked and avoided. Mission controllers catalog tens of thousands of pieces of debris and calculate trajectories. When something large approaches, the station can maneuver. But anything smaller than about 10 centimeters cannot be reliably tracked. That covers the majority of the debris field by count. Small enough to miss, large enough to be catastrophic on impact. The crews live with that knowledge, not as abstract background noise, as a persistent, non-zero, unresolvable condition. The engineering answer to small fast particles is the Whipple shield. The idea is counterintuitive at first. Instead of one thick wall, you use several thinner walls spaced apart from one another. An incoming fragment strikes the outer layer and shatters. The debris cloud from that first impact spreads as it travels toward the inner layers, losing energy at each stage. Each successive barrier absorbs less energetic fragments. By the time anything reaches the innermost wall, the energy has been distributed across many points and reduced enough to stop. The shield works well against the small, fast particles that are most common. Against a large object, it offers little. But large objects are rare, and for the threats the station actually faces most often, the layered design is the practical best answer. Debris risk is one side of living inside a thin shell. The other side is everything the shell is supposed to contain. A spacecraft must supply air, water, and manageable temperatures to the people inside it. Near Earth, resupply missions can replenish whatever runs low. That makes imperfect recycling acceptable. On the ISS, the water recycling system recovers about 90% of all available moisture. Pulling it from urine, sweat, breath condensation, and any other source, running it through filters and processing systems until it is cleaner than most municipal tap water. The crew joke about it. Today's coffee was yesterday's urine. The joke contains an exact description of what the system does. It is not a problem. It is the engineering point. Air recycling follows a similar logic. Oxygen is produced through electrolysis, splitting water molecules into hydrogen and oxygen using electrical current. The oxygen goes into the cabin atmosphere. The hydrogen is handled separately, either vented or run through the Sabatier reaction, a process developed by the French chemist Paul Sabatier in the early 20th century and adapted for spacecraft use. In the Sabatier reaction, carbon dioxide from the cabin atmosphere combines with that hydrogen to produce methane and water. The methane is vented. The water is reclaimed and fed back into the electrolysis system to produce more oxygen. The loop closes imperfectly but substantially. Some air and water are still lost at the margins. Resupply fills the gap. For a deep space mission, resupply is not an option. Every molecule the crew breathes or drinks has to come from what the spacecraft carries or from what the recycling system recovers. The required recycling efficiency climbs from 90% to 98 or 99%. Current systems approach that threshold. Maintaining them without replacement parts, without technicians, without the ability to pause operations while repairs are made, across 2 or 3 years of continuous use, is a different problem from approaching the threshold in a controlled laboratory environment. No mission has yet demonstrated it at full scale. Waste disposal follows the same logic, and the gap is starker. On the ISS, solid waste is packed into cargo vehicles that undock and burn up during re-entry. The atmosphere disposes of it. On a Mars mission, that approach is unavailable. Waste has to be stored indefinitely or recycled entirely. No fully closed waste recycling system for a crewed spacecraft has been demonstrated. The problem is not a hypothetical. It is an unsolved engineering challenge on the critical path to any long-duration human mission beyond the moon. Heat is a less obvious challenge. Spacecraft generate heat from electronics, mechanical systems, and the bodies of the crew. In vacuum, that heat cannot escape through convection or conduction. Radiation is the only mechanism available. The ISS carries large radiator panels deployed from its structure, glowing faintly in the infrared, pushing heat into space as fast as the thermal load demands. In January 2013, one of the ISS cooling loops developed an ammonia leak. Ammonia is the working fluid in the cooling system, and its loss threatened to take down a major section of the station's power and thermal management. Crews performed emergency spacewalks to fix the leak and replace the affected pump module, working in suits on the outside of the station to repair a system that kept the inside habitable. The repair succeeded. But the sequence demonstrated something the engineering had always implied. Every system is load-bearing. None of them can simply fail and be waited out. Now extend the timeline. 6 to 9 months outbound to Mars, months on the surface, 6 to 9 months back. Total mission duration somewhere between 2 and 3 years. Every life support system has to function across that entire span without resupply, without ground crews, without the option of abort and return if something goes wrong in the middle. In 1970, an oxygen tank in the service module of Apollo 13 exploded during the outbound cruise to the moon. An electrical fault triggered the failure. The service module lost power and life support. The crew retreated to the lunar module, a small spacecraft designed to carry 2 people to the lunar surface and back. It became a 4-day lifeboat for 3. The crew rationed water, endured temperatures that fell low enough to produce condensation on every surface, and watched their carbon dioxide levels rise, because the lunar module carried only enough lithium hydroxide canisters to scrub CO2 for 2 people, not 3, for that duration. The solution was a duct tape adapter, improvised from materials on board, that let the command module's square canisters function in the lunar module's round receptacles. All 3 astronauts survived. They made it home through a combination of skill, improvisation, and a particular kind of luck that cannot be planned for. That scenario is famous as a successful failure. The same scenario on a deep space mission would not resolve the same way. No quick return trajectory. No real-time voice contact with mission control. Communication delays measured in minutes. An improvised fix that required precise guidance from engineers on the ground, relayed in seconds, becomes a crew working from documentation, reasoning through contingencies on their own, with no rescue available and no margin for a second failure. The Soyuz 11 mission in 1971 ended differently. On June 30th of that year, during the spacecraft's descent to Earth, a valve opened prematurely. The cabin depressurized at high altitude. The crew was not wearing pressure suits at the time of re-entry, a standard practice under the protocols of that era. All 3 cosmonauts, Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev, died from asphyxiation before the spacecraft reached the ground. The capsule landed on schedule. Recovery crews found the crew dead in their seats. There was no warning, no time for response. The spacecraft had performed correctly in every structural sense. A single valve, opening when it should have remained closed, was the entire chain. The aftermath changed how crewed spacecraft operated. Pressure suits became required during launch and re-entry. Redundant systems multiplied. Checklists lengthened. But the underlying arithmetic did not change. A spacecraft is a thin shell under constant external threat, carrying imperfect recycling systems, maintained by people who are themselves resource limited, operating in an environment that offers no outside help. Each additional day from Earth stretches the consequence of every failure further from any possibility of recovery. The suit keeps one person alive. The spacecraft keeps the crew alive. Both of them operate on the same compressed logic. And everything both of them depend on must still be produced, distributed, and used by the people inside. Now, stretch that mission outward. Keep everything you have just seen, the thin walls, the imperfect recycling, the single valve that killed 3 people, and ask what changes when the distance from Earth is not a few hundred miles, but a few hundred million. The answer is almost everything. The International Space Station orbits at roughly 250 miles up. That number matters for one specific reason. At that altitude, the station sits mostly inside Earth's magnetic field. Radiation exposure is elevated compared to the ground, but the field still provides some shielding. Resupply vehicles can reach the station in a matter of hours. If something goes catastrophically wrong, an emergency return is possible. The crew is, in a real sense, still close enough for Earth to reach back. A Mars mission removes all of that at once. The journey takes 6 to 9 months each way, depending on where Earth and Mars sit in their orbits, relative to each other. During that cruise, the crew is in full deep space, no magnetic field, no resupply, no emergency return trajectory that resolves in hours or days. And there's something else that changes. Something that sounds simple, but reshapes every aspect of the mission. The radio signal itself takes time. Light travels at the fastest speed the universe permits. And light still takes approximately 3 minutes to cross from Earth to Mars at their closest approach. That means 3 minutes to send a message, 3 minutes for the signal to arrive, another 3 minutes for any reply to come back. A 6-minute round trip, minimum. But Earth and Mars do not stay at their closest point. When they are on opposite sides of the Sun, the gap stretches to roughly 20 minutes each way, 40 minutes for a single exchange. Think about what that means in practice. A crew member has a medical emergency. Someone on Earth has an answer. By the time the question travels to Earth, and the answer travels back, 40 minutes have passed. The crew has been managing the situation alone for the entire duration. Every crisis on a Mars mission resolves or does not resolve before Earth can respond to it. Mission control becomes a record, not a lifeline. But the communication delay is only one of the asymmetries that distance builds. The human body was not built for the journey itself. Zero gravity is not neutral. It is an active, ongoing physiological stress. Astronauts on the International Space Station have documented a consistent pattern of effects across missions. Bone density drops. Muscles atrophy from lack of load-bearing work. Fluid shifts toward the upper body, increasing pressure behind the eyes and deforming the shape of the eyeball, producing vision problems that do not always fully resolve after landing. The immune system changes in ways that are still being studied. Astronauts exercise for roughly 2 hours every day aboard the station specifically to slow these processes. They still return weaker than they left. Full recovery takes months. A Mars mission round trip runs roughly 2 to 3 years in total. 6 to 9 months out, time on the surface, 6 to 9 months back. That is years of exposure, not months. Here is where the picture shifts. Mars has gravity, not zero gravity, about 38% of Earth's. That partial gravity is one of the arguments in its favor as a destination. But here is the problem. No one has ever tested whether 38% gravity is enough to preserve long-term human health. The answer is simply not known. The ISS gives us data on zero gravity over extended periods. Earth gives us data on full gravity. What happens to human bone density and muscle mass and cardiovascular function over years at 38% is an open question. The first people to stay on Mars for any extended duration will be finding out in real time, and the radiation exposure over that entire mission adds to a figure already established. Several percentage points of increased lifetime cancer risk. Acceptable in a technical sense for trained volunteers who understand the trade-off. Far from safe in any ordinary meaning of the word. Now consider what they are traveling toward. Mars looks from a distance like a plausible destination. It has a surface. It has days and seasons. Equatorial summer days can reach temperatures around 70 degrees Fahrenheit. That sounds temperate. It sounds like somewhere a person could stand. But here is what the surface actually is. The atmosphere on Mars is less than 1% of Earth's pressure. It is composed almost entirely of carbon dioxide. A human being standing unprotected on the Martian surface would experience embolism and suffocation simultaneously. The atmosphere is unbreathable and too thin to sustain life as a pressure environment. Average surface temperature runs around -80 degrees Fahrenheit. Polar winter temperatures drop to around -200 degrees Fahrenheit. And because Mars has no global magnetic field, and because the thin atmosphere provides almost no shielding, the surface receives a radiation at roughly 250 times the level of Earth's surface. Not slightly elevated, not a modest increase, 250 times. A habitat on Mars cannot sit on the open surface. It needs to be underground, or covered with meters of regolith, the loose rock and dust that covers the planet, to provide radiation shielding equivalent to what Earth's atmosphere and magnetic field supply for free. And then there are the dust storms. Mars experiences dust storms that can grow large enough to cover the entire planet. They can persist for months. During a global dust storm, solar panels lose most of their generating capacity. A colony relying on solar power would face an extended energy crisis with no warning and no short-term solution. Any Mars habitat has to be designed around that possibility, which means the most likely long-term power source for a Mars colony is not solar panels pointed at the sun. It is probably nuclear reactors, which do not depend on sunlight at all. The gap between what Mars looks like from a distance and what it actually is up close is not a small one. People sometimes describe it as the most hospitable other world in the solar system. That is true. It is also a place where the air cannot be breathed, where the surface would irradiate an unprotected person at a rate that would produce serious radiation sickness within hours, where the temperature swings make most of the planet uninhabitable without complete environmental enclosure, and where a dust storm can shut down the power supply for months. And that is only the human body's situation on the surface itself. The deeper question of whether any group of people sent there could become genuinely self-sufficient rather than dependent on resupply from Earth is a separate problem entirely, one that no Mars plan has yet fully resolved. Granted you got there, what would it take to actually stay? Not visit? Not survive for a few months? Stay. The question changes everything. A visitor needs air, water, and food for a fixed duration. A permanent resident needs systems that produce all of those things indefinitely, without resupply from Earth, without outside technicians, without the safety net that every crewed mission has relied on so far. And the moment you begin listing what that actually requires, the scale of the problem comes into focus in a way that most discussions of Mars colonization quietly skip past. Start with food. Mars soil, the loose rock and dust covering the surface, lacks the organic matter and microbial life that Earth soil contains. Plant a seed in Martian regolith, and it will not grow the way it grows in a garden bed. The biological machinery that makes soil fertile on Earth, the billions of organisms breaking down organic matter, cycling nutrients, binding particles, is simply absent. A Mars colony would need to build that from scratch. Controlled growing environments, manufactured nutrients, closed-loop agricultural systems, not a farm. A factory that produces food the way a spacecraft produces oxygen through deliberate engineered process every single day. Oxygen comes from ice. Mars has water ice, locked in its polar caps and buried beneath the surface in certain regions. Extract the ice, melt it, run electrical current through the water, and the molecule splits into hydrogen and oxygen. The oxygen goes to the habitat. The hydrogen can be recaptured and used for other reactions. It works, but it requires energy to run continuously, machinery that cannot break down, and a power source that does not depend on sunlight. Which brings the problem back to dust storms. A colony that runs on electrolysis for oxygen and dust storms can shut down the power for months is a colony that eventually runs out of air. Nuclear reactors are the likely answer, not solar panels. Reactors that generate heat and electricity regardless of what is happening in the sky above. Then, manufacturing. Every component a colony uses will eventually wear out. Seals degrade. Filters clog. Circuits fail. On Earth, you order a replacement. On Mars, at minimum, you have a 6-month wait for a resupply mission to arrive, and only if one was already planned and launched before your component failed. A genuinely self-sufficient colony cannot depend on waiting for parts from another planet. It needs the capacity to fabricate, repair, and replace critical systems using local materials. That is an industrial capability. It is not a workshop. It is closer to a small civilization's manufacturing base, built from scratch, on a world where every input has to be extracted, processed, and converted before it can be used. Medical care follows the same logic. A crew of explorers can bring medications, surgical supplies, and trained personnel for anticipated emergencies. A permanent settlement will eventually face everything: trauma, childbirth, surgical emergencies, chronic illness, cancer, the full range of human medicine, practiced without the ability to evacuate patients to a larger facility, and the social dimension cannot be separated from the engineering one. A community under permanent environmental stress, unable to leave, dependent on every other member for survival, governed by rules they have to write themselves, is a political and psychological entity as much as a technical one. History suggests that small, isolated human groups under extreme pressure are not naturally stable. Here is the point that is easy to lose in the excitement of the idea. A colony that cannot produce its own food, air, water, energy, and manufactured goods without regular resupply from Earth is not a backup for humanity. It is an outpost, a distant research station, not a second branch of civilization, not insurance. To become genuine insurance against catastrophe on Earth, a Mars colony would have to be able to survive the complete, permanent loss of contact with Earth and keep functioning. That threshold is not years away. It is generations away. Perhaps many generations. No credible engineering timeline currently puts it closer than that. Which raises the question of why send humans at all. Robotic missions have mapped the surface of Mars, drilled into its rocks, analysed the chemistry of its soil, and done so without life support, without food, without psychological care. The science argument for humans rests on adaptability. A robot follows its programming. A human can notice something unexpected and change plans on the spot, make judgment calls under ambiguous conditions, improvise solutions to problems no one anticipated. The inspirational argument is harder to quantify, but probably real. Something about a human standing on another world reaches people in a way that telemetry from a rover does not. Whether those arguments justify the cost and risk is a question that different people answer differently. But the argument that Mars is near-term civilizational insurance does not hold up to the numbers. The longer argument, the one that actually justifies thinking about spreading off Earth, operates on timescales that are difficult to hold in the mind. Earth is not eternal. The Sun is roughly halfway through its main sequence life. The long, stable phase in which it burns hydrogen in its core. It has approximately 5 billion years of hydrogen burning left. At the end of that phase, it will expand into a red giant and consume the inner planets. But the countdown to uninhabitable Earth is far shorter than that. The Sun brightens by roughly 10% every billion years as it gradually increases its energy output. In approximately 1 billion years, that brightening will be enough to evaporate the oceans. Not gradually reduce them. Evaporate them. The water that covers most of Earth's surface, the water that every living thing on this planet depends on, will simply be gone. That is the longer fuse. The shorter ones are harder to plan around. A large asteroid, roughly 6 miles across, strikes Earth approximately once every 100 million years. The last one hit 66 million years ago. It ended the age of dinosaurs and eliminated roughly 3/4 of all species on Earth. If one of that scale arrived today, human civilization would not survive it. We track many near-Earth objects, but tracking is not deflection, and smaller asteroids, hundreds of meters across, are far harder to find. We would not necessarily see one coming. Yellowstone sits above one of Earth's largest volcanic hotspots. It erupts on a rough cycle of about 600,000 years. The last eruption was approximately 640,000 years ago. A full Yellowstone eruption would blanket large portions of North America in ash, disrupt global climate, and devastate agriculture across much of the planet. These are not science fiction scenarios, they are geological facts. And then there are the risks we make ourselves: nuclear war, engineered pathogens, runaway climate change, accidents from technologies that do not yet exist but are coming. The argument for becoming a spacefaring species is not that Mars is close or easy or hospitable. It is that concentrating all human life on a single world, subject to all of these risks simultaneously, is a strategic vulnerability. Insurance, by definition, costs something before you need it. The outer solar system offers worlds with water but almost nothing else in terms of practical colonization. Europa, the moon of Jupiter, has a liquid ocean beneath its ice shell. Enceladus, orbiting Saturn, vents water vapor from beneath its surface. Titan, Saturn's largest moon, has lakes and rivers, though they are liquid methane, not water. These are extraordinary places scientifically. But Jupiter is roughly 6 years away with current propulsion. Saturn is roughly 7. The sunlight reaching Jupiter is about 4% of what reaches Earth. At Saturn, it drops to about 1%. Europa's surface temperature runs around negative 270 degrees Fahrenheit. Jupiter's radiation belts bombard its moons with intense particle radiation that would be lethal to unprotected humans. These are exploration targets, not places humans are moving to within any time frame that matters to the current species survival conversation. Which brings the calculation back to the people who would actually make these journeys. Because none of the engineering questions are the hardest ones. The longest continuous human spaceflight on record was completed by the Russian cosmonaut Valery Polyakov, who spent approximately 14 months aboard the Mir space station in the mid-1990s. By most measures, he did remarkably well. He returned physically weakened, as every long-duration astronaut does, but psychologically intact. He is held up as evidence that the human mind can handle extended isolation. But there is a detail in that story that matters. Polyakov was in low Earth orbit. He could see Earth out the window. He could speak to his family in something close to real time. He was never more than a few hundred miles from home. A Mars mission is qualitatively different. Not quantitatively different. Qualitatively. As the spacecraft moves away from Earth, the planet shrinks. First it is a disk. Then it is a bright point. Then it is a star, indistinguishable by eye from the other stars around it. The place you came from, the only home your biology knows, becomes a point of light you could cover with your thumbnail. And the communications that connect you to that light are not conversations. They are messages. You send something. You wait 6 minutes at minimum, 40 minutes at maximum, for a reply. There is no phone call. There is no voice saying in real time that everything is going to be fine. There is a delay, and then another delay, and then a recording. ISS crews, even with a view of Earth and real-time family contact, experience interpersonal conflict, depression, motivation loss, and sleep disturbances. These are documented effects from missions lasting 6 months, on a station where resupply arrives regularly and emergency return is always possible. Earth analog isolation studies, conducted in facilities designed to simulate deep space conditions on the ground, show the same patterns: conflict within the crew, monotony, a gradual erosion of motivation that sets in even when participants know they can leave. No rescue is available. No, the whole thing is voluntary and temporary. Remove those safety nets and extend the duration to 2 or 3 years, and no one knows with certainty what happens to the human mind. Some researchers believe the psychological challenges are manageable with the right crew selection, the right training, the right mission structure. Others believe that multi-year deep space isolation will produce breakdowns that cannot be anticipated or prevented. Both groups are speculating. There is no data. The first multi-year deep space crew will not be validating a model. They will be generating one. They will be the pioneers who discover, in real time, what the human mind can and cannot endure at the far end of the communication delay, with Earth a star behind them and nothing but distance ahead. That question has no answer yet, and the mission that answers it is still coming. Now imagine going further, past Pluto, past the heliopause, past the last faint warmth of the sun, past every boundary this script has traced so far, out into interstellar space, where there is no nearby star, no light, no heat source, nothing to intercept the cosmic rays arriving from every direction. The temperature of that void settles near the cosmic microwave background, a few degrees above absolute zero, roughly negative 454 degrees Fahrenheit. Not cold in the way a winter morning is cold. Cold in the way that almost all molecular motion has stopped. The nearest star is Proxima Centauri, part of the Alpha Centauri system. It sits 4.24 light-years away. That is approximately 25 trillion miles. The number resists ordinary comprehension. So consider this. Voyager 1 is the fastest outbound spacecraft humanity has ever built. Right now, it is crossing through the outermost edge of the solar system, having traveled for nearly 50 years. At that speed, a ship aimed at Proxima Centauri would arrive in roughly 70,000 years. Not 70,000 days. Not 700 years. 70,000 years. Agriculture is about 12,000 years old. Written language is about 5,000 years old. Modern science is a few hundred years old. Proxima Centauri, at our fastest existing speed, is more than 5 times the age of human civilization away. But the answer was stranger than expected. Every proposed solution to the speed problem creates a new problem of its own. Faster propulsion concepts exist on paper. A fusion rocket would fuse hydrogen into helium and channel the reaction energy to accelerate exhaust to perhaps 10% of the speed of light. That would reduce the journey to roughly 40 years. The catch: we have not built a fusion rocket. We have barely achieved net energy gain fusion in a laboratory, producing slightly more energy out than went in. The rocket itself remains theoretical. An antimatter drive would be more powerful still. Matter and antimatter annihilate each other completely, releasing energy in a density no chemical or nuclear fuel approaches. The problem is production. All the antimatter humanity has ever accumulated would fit in a space too small to see with the naked eye. Producing enough for an interstellar mission would cost more than the entire global economy, by orders of magnitude. Not slightly beyond reach, effectively impossible with any foreseeable technology. Then there are laser-pushed light sails, perhaps the most credible near-term concept. A vast laser array on Earth, running at hundreds of gigawatts, pushes an ultralight sail, miles across but massing only grams, to 10 or 20% of the speed of light. For a small unmanned probe, this might work. For a crewed mission, it cannot. The crew, the life support, the shielding, the supplies, the habitat, all have mass. The laser cannot push that mass to the required speeds. The math closes only if almost nothing is on board. And then there is the deceleration problem. A laser from Earth can accelerate a sail outward. It cannot reach the destination to slow the ship down. Slowing requires onboard fuel, which adds mass, which reduces the speed the laser can achieve. A flyby works for an unmanned probe. It does not work for people. People need to stop. So let's say a fusion rocket is built someday. Let's say it achieves 10% of light speed. The journey to Proxima Centauri takes 40 years. The crew that launches would be elderly or dead before arrival. The mission cannot be crewed by one generation. The solution that follows from this logic is a generation ship. A vessel large enough to sustain a community. People living aboard, reproducing, aging, dying, in transit. Children born in space who have never seen Earth. Grandchildren who inherit a mission they had no role in choosing. The practical demands multiply quickly. A closed ecosystem must function continuously for 40 years or more without resupply and without outside engineers to repair it when it fails. The population must be large enough to prevent inbreeding across multiple generations, while small enough to be sustained by the ship's resources. Social cohesion must survive across decades of confinement, through grief, conflict, and the slow generational drift of culture. Power must be available continuously. Voyager's radioisotope generators still produce electricity after 45 years, but at hundreds of watts. Life support for a ship community requires megawatts. A megawatt-scale nuclear reactor, running reliably for decades in zero gravity, at temperatures that swing between extremes, with no maintenance crew from outside, is an unproven technology. No such reactor has ever been built and operated under anything like those conditions. Radiation in interstellar space adds a further constraint that has no clean resolution. Beyond the solar system, there is no stellar wind. no magnetic field to deflect cosmic rays. The full galactic flux arrives unimpeded from every direction. Heavy shielding reduces the dose, but heavy shielding means more mass, and more mass means less speed, and less speed means longer transit time, and longer transit time means longer total radiation exposure. The shielding that would help is also the mass that would hurt. The problem folds back on itself. Wait. More shielding makes the radiation problem worse, not in every case and not without limit. But the trade-off is real. Adding meters of water or hydrogen-rich material to a ship's hull adds thousands of kilograms. Those kilograms reduce achievable velocity. At 10% of light speed, every additional year of transit is another year of full cosmic ray exposure. The equation does not have a comfortable solution. And then there is the ethical dimension, which may be the hardest part. The people who launch on a generation ship choose to go. Their children do not. Their grandchildren do not. Everyone born on that ship inherits a mission they cannot escape. Turning back at year 20 means another 20 years to return. There is no leaving at the next stop. There is no opting out. Philosophers and ethicists have written extensively about whether it is acceptable to commit future generations to conditions they never consented to, in circumstances they cannot leave. No clear answer has emerged. The question would have to be resolved, somehow, before any such mission could begin, assuming the technology ever exists to make it necessary. Set all of that aside for a moment. Step back from propulsion and shielding and ethics, and ask the simpler question underneath. What does all of this mean? It means that deep space is not a difficult environment humanity must learn to navigate. It is an environment that does not accommodate human life at all. Biology evolved on Earth, under specific conditions, over billions of years. It assumes those conditions. It does not function when they are removed. A spacecraft or a suit mimics Earth, partially, expensively, fragilely. It is a bubble of Earth conditions carried into a place where those conditions do not exist. The bubble is the life support. Outside the bubble, the universe is indifferent. Physics does not negotiate. Pressure operates by laws that do not adjust for human needs. Radiation operates by laws that do not adjust for human needs. Temperature operates by laws that do not adjust for human needs. An unprotected person in space dies in seconds. Not from a failure of courage or will, but because the physical laws that govern matter and energy have no provision for human survival. The cinematic image of a person drifting peacefully in space is fiction. The reality is rapid, cascading physiological failure. Astronauts trust their lives to engineering, and even with the best engineering, risk cannot be eliminated. We don't know yet whether all the challenges described in this script are solvable, whether closed-loop life support can be maintained for decades without resupply, whether shielding can be made effective without prohibitive mass, whether the human body can tolerate partial gravity for generations, whether the human mind can endure multi-year isolation beyond the communication delay, whether faster-than-light travel is physically possible at all, or whether the universe simply does not permit it. Some of these questions may have answers within a century. Others may not have answers ever. What we know is this. Other habitable worlds may exist around other stars, rare scattered islands in a vast ocean of hostility. But reaching them with current technology takes tens of thousands of years, and reaching them with the fastest technologies we can conceive of takes generations. For now, and for the foreseeable future, deep space is a place humanity can visit briefly, at enormous cost, with extensive support, for limited durations. It is not a place to live. Earth is the exception, not the rule. The only world in the known universe where a human being can step outside and breathe the air and stand in sunlight and drink water from the ground without a system between them and death. That is not a small thing. That is the entire foundation of every life that has ever been lived. Every city built, every child raised, every question asked about the stars above. All of it resting on one thin layer of atmosphere, one magnetic field, one distance from one star, one set of conditions that happen to hold for long enough for biology to find its shape. That question, of whether those conditions will hold, and for how long, and what we owe to the world that made us, is the one that doesn't end when the lights go down.